On with Unit 1 in this video, and this video is going to focus on learning Target 2D, which is all about families of functions. By the end of the lesson, you will be able to, given an equation, describe the transformations that have taken place, and given a parent function and a description of the transformations, write a new equation to represent those transformations algebraically. So what is a family of functions? A family of functions starts with a parent function, and a parent function is the simplest form in a set of functions that forms a family. In this video, we're going to use f of x to represent our generic parent function, and later on throughout the semester, we're going to continue to revisit this concept when we learn about different parent functions. Now, each function in that family is a transformation of a parent function. So a transformation is some change that has happened to the original parent function f of x, and in this video, we're going to learn about 3 different types of transformations. The first transformation we're going to talk about is a translation or a shift. Now we could shift a graph either horizontally, vertically, or both. We're going to start with the vertical translations or the vertical shifts. So here in our graph, I have 3 graphs that all have the exact same shape. In the middle here, I have this black curve, which we're going to represent as f of x. This is our parent function here, and I'm going to put 1 point on the graph, which is 0, 0. Now, when we translate a graph vertically, it's like if we get in an elevator and we take an elevator and go up so many stories, or if we get in an elevator and go down so many stories. We don't change, the shape of the graph still stays the same, but what's happening as I shift up or down, my y coordinate is changing. So if we were to shift this graph up, then what we would be doing to f of x, our original function, is I would be adding so many values to that function f of x. And we're going to say that we go up k units. So this point 0, 0 on the graph is now being moved up to the point 0, k. Since we have moved this graph up k units, it is the y coordinate that is changing. Algebraically, how we represent that would be our original function f of x, and we're adding k to that. Remember, f of x is our y coordinate. That is what y is equal to, and I want to add k to all of those y coordinates to move this graph up. Likewise, if I wanted to shift a graph down k units, I could move our original point 0, 0 down to 0, negative k, since I have shifted this graph down, just like when we get in an elevator if we go down so many stories. Algebraically, we can write that as f of x minus k. Since we are moving the graph down, we're going to subtract k from that. Down below, what I have here is a summary of this, and we're going to look at different parent functions throughout this year, and that would take the place of what this f of x is representing in general. So if we're up k units, we have our new function would be y equals f of x plus k, and on a coordinate level, what's happening is that we are adding k to all of the y coordinates. If we shift our graph down k units, then our new equation would be y equals f of x minus k, and we are subtracting k from all of those y coordinates if we look at the actual coordinate pairs of what's happening. Something else I want to point out here is that this plus k or this minus k is happening outside the function. So f of x itself is not changing. I am just either adding or subtracting a number to that. When we look at horizontal translations next, we're going to notice that this transformation takes place inside the function. So we're going to talk a lot in this video about the difference between being inside or outside a function. We are inside a function if we are changing the x itself, so inside the parentheses of f of x there, and we are outside a function if we are adding, subtracting, multiplying, or dividing to the entire f of x itself. So for our vertical translations, that is happening outside the function by either adding k to represent going up so many units, or subtracting k to represent going down so many units. Let's look at horizontal translations. So our horizontal translations would be if we want to shift a graph to the right or to the left. So on our graph here, I have a parabola, and in black, that's representing our parent function right here. That is our original base function that we're starting with. And I've taken the graph and shifted it to the right, and I get this blue curve here. Or we could shift the graph to the left and we get that green curve. Just like with vertical shifts, the shape is staying the same. Nothing's changed here. I still have a parabola. I'm just shifting it either to the right or to the left. And since I'm going to the right or the left now, it is going to be the x coordinate that changes versus before it was the y coordinate that changed. Now before we look at the equations, let's talk about what the general form for a horizontal shift would be. So in general, when I shift a graph, that's happening inside the function since I'm changing that x coordinate on my graph. So I have to be doing something inside the parentheses to that x coordinate. In general, if I want to shift any function, it would be f of x minus a number. Now, if that number I sub in is positive, then I'd be going to the right. And if I sub in a negative number, I would be going to the left. What makes this a little confusing is that when I sub in a positive number here, I actually end up with a negative sign in my final answer because I get f of x minus that positive number. So when we're moving to the right, we're starting with f of x minus, but because I want to move to the right here, I'm subbing in this positive value h, and that would move the graph over h units to the right. Versus if we sub in a negative number and we have f of x minus and we sub in a negative h value, when we simplify that, we get f of x plus that h. And I know this looks really confusing because you're thinking, wait, if my answer has a minus, shouldn't I be going to the left? If my answer has a plus, shouldn't I be going to the right? And it all goes back to the general form that we have up here, where for any horizontal shift, we start off with f of x minus that number. And when we sub in a number and that number is positive, like in this case where we're going to the right, we do end up with a negative sign in our final answer since I subbed in a positive number into the x minus and I sub that into that spot there. Versus when I sub in a negative number, such as the negative h, which would move me to the left, the double negative here makes my final answer in the equation be a positive. On a coordinate level, what's happening though is exactly what we would think. If I want to move to the right, I need to be adding h to all the x coordinates because I'm moving in the positive direction to the right. If I want to move to the left, I am going to be subtracting h from all of the x coordinates since I want to move in the negative direction. It all goes back to the fact that our original setup here for any horizontal shift has a negative sign in it. And so when I sub in a positive number, it still is an x minus that number. And when I sub in a negative number, which means I'm going to the left, I end up with the double negative, which makes it be f of x plus h. The other difference here than our vertical shifts before was that all of this is happening inside the function. It's the x itself that's changing, not the entire f of x. So when I was talking about inside and outside the function before, inside the function is inside this parentheses of f of whatever I have versus adding or subtracting a number to the entire f of x function itself. So to recap, if I want to shift a function horizontally to either the right or to the left, that transformation is happening inside the function. If I want to go to the right h units, my new equation would be y equals f of x minus h. And on a coordinate level, I would be adding h to all of the x coordinates. If I want to shift my graph to the left h units, I would end up with the equation y equals f of x minus a negative h, which is simplified down to be f of x plus h, and I'm subtracting h from all of the x coordinates. Let's look at a couple examples where we can put together some vertical shifts as well as some horizontal shifts. So in our first set of examples, we are going to assume that our parent function is y equals x cubed. So instead of using f of x, I'm going to use x cubed to represent my f of x. And for each of the equations below, we want to describe the transformations that are happening. So I can see in all of these examples that I have this cubic power in them, and that's coming from the parent function. All of the transformations is all of the extra stuff that is happening to either the x cubed or happening to the x. Let's look at our first example. Here we have y equals x cubed plus 4. In this case, the extra stuff that is happening is that plus 4, and that plus 4 is being added to the entire x cubed here. Because of that, we say that this is happening outside the function. The entire x cubed is getting 4 added to it versus just having x being added, having 4 added to it. Because that happens outside the function, this is a vertical shift. Since we are adding 4, this is telling me that we are going up 4. So our transformation here then would be up 4. Let's look at example 2. So in example 2, we have y equals x cubed minus 10. Again, the x cubed is our parent function, so the extra stuff that is happening here is coming from that minus 10. Now, is that minus 10 happening inside or outside the function? So that minus 10 is happening outside the function since it's being subtracted from the original x cubed. That tells me that this is going to be a vertical shift, and the fact that we are subtracting 10 means that we are going down 10. Let's look at example 3. So in example 3, we have y equals x minus 1, that entire thing cubed. So the cube power is still here. The change now, though, is this minus 1 that is happening inside the parentheses. And because that's inside the parentheses, we say that this is inside the function. Since it's part of the x itself, so instead of having our original x, we now have an x minus 1 that has replaced that. Since this transformation is happening inside the function, this is one of our horizontal shifts. So this is either going to the right one or to the left one. In this case, if we go back to our right and left shifts that we had from up above, if I have a x minus a number, that is one of our horizontal shifts to the right. So in this case, we have moved to the right one. And remember, that's happening because the general form for a horizontal shift is f of x minus the number. And we want to just take the number itself, and ultimately what we're doing is we're flipping the sign here, and so we're, instead of looking at -1, I'm looking at +1, and that's telling me that I'm moving to the right. Let's look at example 4. So in example 4, we have y equals x plus 5, the entire thing cubed. Again, that cube power is coming from our parent function. The transformation is happening from the extra stuff. So that's happening from that x, that plus 5 that is being added to the x. Is that plus 5 happening inside or outside the function? So that plus 5 is happening inside the function since it's inside those parentheses. So that tells me that I have a horizontal translation. So I'm either going to the right or to the left. In this case, since I have x plus 5, I could actually rewrite that as x minus a -5, the entire thing cubed. And from here, I can see that the number that got subbed in is actually a -5 value, which tells me that we are going to the left 5 then. Let's look at example 5. So in example 5, we have y equals x minus 2 cubed minus 8. So we have a couple more things happening than in examples 1 through 4. So now I not only have this -2 that's happening inside the function, but I also have this -8 that's happening outside the function. Why don't you guys pause the video and list what each one of those transformations is doing. So the -2, that's happening inside the function, so that's going to be a horizontal shift, and that is going to be a horizontal shift to the right 2, since that 2 itself is subbed into that x minus equation. The -8 is happening outside the function, so this is a vertical shift going up or down, and in this case, since we're subtracting 8, this would be a vertical shift that is going down 8. Okay, and in our last example here, we have x plus 3 cubed plus 6. Why don't you guys pause the video and list all of the transformations that we have in this last example. So the two things that I see happening here is that plus 3 as well as that plus 6. In this case, the plus 3 is happening inside the function because it's inside that parentheses. It's being raised to the third power as well. So this is a horizontal shift. And in this case, that x plus 3, remember, we can rewrite as x minus that -3, which tells me that we are going to the left 3 then. The plus 6 is happening outside the function, and since we're adding 6, we know that we are going up 6. And it's a vertical shift because that addition is happening outside the function. Let's look at some examples where let's flip what we're doing. So here we were given the equation and we were asked to list the transformations. Well, what if now we're given the transformations and we want to list the equation that goes with those? So for these examples, we're going to assume that the parent function is now going to be x squared. So instead of being x cubed, we're looking at x squared. So this would be our generic f of x. And we're given a couple transformations for each one of these. So in example 7, we have the transformation right 12. So if we're going to the right, is that transformation happening inside or outside the function? So if we're going to the right or to the left, that's a horizontal shift, and that happens inside the function. So our equation then, I need to have that be inside that x squared. So I'm going to put some big parentheses and put the square on the outside. Remember, we always start off with x minus as our horizontal shift equation. And since we're going to the right, I'm going to substitute in that positive 12, which leaves us with x minus 12, the entire thing squared. Let's look at example 8. So in example 8, we're going up 5. So that would be a vertical shift. Do vertical shifts happen inside or outside the function? So our vertical shifts happen outside the function. And what that tells me that is that the x squared is not going to change. There's going to be nothing different that's inside that square. I'm going to get left with an x squared. But since I'm going up 5, I want to add 5 to that entire x squared. Let's look at example 9. So in example 9, we're going left 3 and up 2. So we've got more than one transformation happening here. Why don't you guys pause the video right now and decide which of those transformations are happening inside the function and which is happening outside the function. So the left 3 is a horizontal shift that happens inside our function versus the up 2 is happening outside our function. So when we go to write this out, we're going to have a couple more things here. So let's set up our general equation. Our parent function is x squared. So I'm going to start off with parentheses that have the x minus inside, then the square. The fact that we are going left 3 tells me that I am substituting in a negative 3 inside that function. And the plus 2 happens outside the function, and I'm adding 2 to that. Now, if we would like to simplify this, of course, we could rewrite this as x plus 3 squared plus that 2. Okay, let's look at example 10. So in example 10, we're going right 1 and down 7. Why don't you guys pause the video and write out your equation for example 10. So when we go right 1, that's happening inside the function since that's a horizontal shift. And down 7 is happening outside the function since it's a vertical shift. When we go to write this out then, remember x squared is our parent function, so I'm going to start off with x minus the whole thing squared. Since we're going to the right, I'm substituting in the number itself, so I get x minus 1. And then since we're going down 7, we're subtracting 7 from the outside of that equation. Let's look at example 11. Why don't you guys pause the video and write out your equation for example 11. So here we're going right 4 and up 3. So let's write out our generic starting. Our parent function is still x squared, so I have x minus something squared. The right 4 is telling me I'm substituting in a positive 4 inside that function. And up 3 means that we are adding 3 to the outside of that parent function. Let's look at example 12. So we're going left 7 and down 1. Why don't you guys pause the video and write out your equation for this guy. So our left is a horizontal shift, so that means that's happening inside the function. So when we start setting this up, I still have the x squared as my parent function. Because we're going to the left, I'm subbing in a negative value into that. And then the down is happening outside since that's a vertical shift, and we'll be subtracting off 1. Of course, just like before, we could rewrite this as x plus 7, the entire thing squared minus 1. And it would be a good habit to start simplifying your answers where instead of writing the double negatives, we just write it as x plus that number. So far we've looked at shifts, both vertical and horizontal shift. Our next type of transformation we're going to look at is reflections. And we have two types of reflections. The first one is going to be a reflection over the x-axis. So here we have this little graph that's comprised of two line segments. So we have these 3 points on our graph, and we're shifting that over the x-axis. So this graph is flipping down and around to this blue graph in quadrant 4, which is the same shape still. So I still have lines connecting, but it's just been flipped upside down now. And when we do that, when we reflect over the x-axis, the x values do not change, but the y values are actually multiplied by a -1. And in this case, we can see that all of our y coordinates have become negative since they got multiplied by that -1 value. How we write that out algebraically is, since we're multiplying the y values, I am multiplying the outside of my parent function. So remember, f of x is our parent function, and I'm multiplying that by this negative outside this function. So just like before, when we were dealing with the y coordinate changing, that is happening outside our parent function of f of x. So we get that negative sign in front. So this graph down here I could represent with negative f of x then. Let's look at our other reflection. So if we reflect over the y-axis, instead of flipping this graph upside down, I'm now flipping this graph over. So I took the same parent function graph here, and I've now flipped it over the y-axis. When we reflect over the y-axis, the y values do not change, but the x values this time are the ones that are being multiplied by a -1. And so we can see on all of our coordinates then that all of the x coordinates have now become negative. Since this is affecting the x values this time, the negative that gets multiplied is happening inside that function. So before, with our reflection over the x-axis, we were multiplying the negative to the entire f of x, since that entire f of x, remember, was our y value that we started with. But now when we reflect over the y-axis, it is the x variables that are changing, or our x values that are changing. So I need to multiply inside the function to the x itself directly, which gives me f of -x. So if I were to write this out over here, this graph in green would be represented with f of -x. Okay, before we do some examples with reflections, I want to talk about our last type of transformation. And our last type of transformation is our vertical stretches and compresses. So our vertical stretch or compress, I like to think about this as a slinky. It's what happens if I extend a function out or if I collapse a function back down. Since this is a vertical stretch or compress, this is changing the y coordinate. And for both of these, what's happening is that we are actually multiplying all of the y values by this a factor, or this letter number a, and a is what we call the stretch or compress factor. So in both of our cases down here, we see I have y equals a times f of x, and how we determine if we're stretching versus compressing depends on what that value of a is. If a is a value that is bigger than 1, then what we're doing is we're actually stretching this graph because I'm multiplying by some value that's larger than 1 and it's stretching that graph vertically, versus if our a value is less than 1 but greater than 0 still, we are compressing this graph down. Now the reason we have this restriction about a being greater than 0 for a vertical compress is that if a was negative, we would actually have another transformation. So if a was a negative number here, not only could we have a stretch or compress, but we also have another transformation. What other transformation would be happening if that a value is negative? Well, if that a value is negative, we have a reflection over the x-axis. Because remember, if we scroll back up, our reflection over the x-axis happens when we multiply by a negative sign outside of our function f of x. And this a value is also being multiplied to f of x, and so if that a value is negative, then it's not only maybe a stretch or compress, but it's also a reflection over the x-axis. Now, the order in which we apply these matters. And in later sections, we're going to look at how can I now use this to help me graph. Right now, we're looking at graphs to get an idea visually of what's happening, but I haven't really done any examples with graphing, and we're going to see those in some later sections. But when we start to apply these transformations, the order absolutely matters. And the reason the order matters is the same reason why when we simplify stuff algebraically, we have order of operations. So when we simplify and we apply these transformations, we always want to work from the inside to the outside part of the function. And what that means is anything that's affecting inside our function, so anything that's affecting x directly, needs to be applied first. And then from there, we're going to work our way out until we end up with the values on the far outside of f of x. So that first one that we would have would be our horizontal translations. These are our shifts that go right or the shifts that go to the left. And remember, that was the only one that was happening inside the function. So we want to make sure that that gets applied, or not the only one, but it is happening inside the function. So we want to make sure that that gets applied first. From here, we have our vertical stretch or compress, and I can actually group my reflections into this. So the order in which we apply the vertical stretch or compress with our reflections could flip-flop. Our vertical stretch or compress is happening outside the function, and that's what we're multiplying y to be. So that would be our next one. So this is that a value that we have that we'll look at in some examples. The next one is our reflection, and this could be either a reflection over the x-axis, the y-axis, or both. We would apply those next. And then lastly is our vertical translations, and those are our shifts that are going up or down. We always want to make sure that we apply our vertical translations last, and specifically, we need that vertical stretch or compress / reflections to always come before those vertical translations. Now let's look at some examples with these new transformations. So in this first set here, we're going to assume that our parent function is back to being y equals x squared. And for each of these equations that we're given, we want to describe the transformations that are happening. So in this case, our first example, we have 3x squared. Our parent function is that x squared, so the 3 is the extra stuff here. Now, unlike before with our horizontal and our vertical shifts, 3 is being multiplied now. 3 is that a value that we had. And in this case, this would be a vertical stretch by 3, since 3 is bigger than 1. So we have a vertical stretch then by 3. And just like we did before with the shifts up, down, left, or right, we want to state how many units we're changing this by, so we are stretching by 3. Let's look at our next example. So we have -1/2 x squared. X squared again is our parent function, so the numbers that are being multiplied in front is all the extra stuff. In this case, we actually have two transformations though. The negative sign and then the 1/2 itself is providing two different transformations. Let's start with the 1/2. So in this case, that 1/2 is going to be a vertical compress by 1/2 since that value is less than 1. The negative sign is a reflection. And is it a reflection over the x-axis or over the y-axis? What do you guys think? So this would be a reflection over the x-axis since that negative sign is outside the function. Axis. There we go. Let's look at example 15. So here we have -5 x squared plus 7. So we have quite a few things going on here. We have the -5 that's being multiplied as well as the plus 7. How many transformations do you guys think we have in example 15? We actually have 3. And we're going to want to list these in order to get some practice. So the first one would be any horizontal shifts. Now I have none of those since I just have x to the second, but I do have a vertical stretch or compress. Is that going to give me a vertical stretch or a vertical compress? So in this case, we have a vertical stretch by 5, since 5 is bigger than 1. And the negative sign, remember, that's our reflection over the x-axis. So that's our second transformation. And then our last transformation is that plus 7 that is happening outside the function, and that is telling me that we are going up 7, and that is our vertical translation. So it's a good idea to have this list in the order in which we apply them, because we can kind of go through and check off and see, well, do I have any of this type? No, okay, do I have any of this type? And go through our list from there. Let's look at our next example. So here we have negative x, the entire thing squared. So this is a little bit different. The negative sign now is inside the parentheses. That's going to make a huge difference. Since it's inside the parentheses, this is now a reflection over the y-axis. And that is our only transformation for that one. Now, what about example 17? Why don't you guys pause the video and decide on what your transformations are. So in example 17, I see two things. I see the 4 in front as well as that minus 3 that we have here. So our first one would be any horizontal translations. That minus 3 is a horizontal translation since it's happening inside the parentheses. So it's attached to that x there. And in this case, remember, our horizontal translations are x minus the number. So since the number itself here is a 3 that was substituted in, we are moving to the right 3 then. Now the 4 in front, that would be a vertical stretch since that value is bigger than 1. So we also have a vertical stretch by 4. Now let's look at example 18. So why don't you guys pause the video and decide on all your transformations for problem 18. So in 18, I see a couple things. We have a negative sign in front, a plus 2 inside the parentheses, as well as that minus 10 outside. So in this case, we're going to have 3. Our first one would come from any horizontal shifts, and that would be that plus 2. Now in this case, remember our formula for horizontal shifts is x minus the number, so we have x minus a negative 2, which tells me that we are actually going to the left 2. Our next one would be any stretches or compresses, and that would come from the number that's multiplied in front of the parentheses. Now in this case, I have a negative sign. Technically it's a negative 1, but that value itself is not bigger than or less than 1, it's just 1 itself, so we have no stretches or compresses, but the negative sign is producing a reflection over the x-axis. And then last up is that minus 10 that is outside the function furthest away, and that is our vertical shift that has gone down 10. Okay, a couple more examples. So let's just shift gears and work backwards again. So this time we're going to be given the transformations and we want to come up with the corresponding equation to that. And we're going to make this a little bit different this time again. So instead of our parent function being x squared or x cubed, we're going to look at what happens if our parent function is y equals the absolute value of x. And this is actually leading us into what our next section will be, where we'll look at our parent function that is always going to be the absolute value of x. So we're going to get some practice for that right now as well. So in all of these equations, then when I go to set this up, I'm going to have these absolute values, and then I'm going to have x maybe minus or plus a number inside. So I'm going to just set up my general form that I have. And let's read each transformation. The first one we have here is a vertical stretch by 5, right 4, and down 7. Well, let's take it one at a time. So a vertical stretch by 5, that's happening outside the function, and that tells me that my a value here is 5, so I want to multiply 5 in front of the absolute values. Right 4 is happening inside the function, and since I'm going to the right 4, I'm going to sub in a positive 4 into that x minus equation. And then down 7 happens outside the function, and we would be subtracting 7 from the end of that. Okay, let's look at example 20. So we have left 3, up 10, and a vertical compression by 2 over 7. Why don't you guys pause the video and write out what your equation for this guy would be, and I'll start you off with kind of the general form, and you guys can fill in from there for this parent function being the absolute value of x. So let's check this. So our first one being left 3 tells me that I need to sub in a negative 3 inside the function. So that left, right always happens inside. Because it's going to the left, I'm subbing in a -3. Up 10 happens outside the function, and I'm adding that number to it. So I get plus 10 outside the absolute values. Then the last one is a vertical compressed by 2/7, and that works the same as a vertical stretch. The difference here is that the number is just smaller than 1, but I'm still multiplying by that a value, which is 2/7. And of course, if we want to kind of simplify this down, we'd get 2/7 absolute value of x plus 3 plus 10. Now in example 21, we have a reflection over the x-axis. We're going to the left 2, and we have a vertical stretch by 3. I'm going to set up our kind of general form here with our parent function. Why don't you guys pause the video and write this out using all those transformations. So let's check 21. So a reflection over the x-axis, that's when we multiply by a negative outside the function, because a reflection over the x-axis is not changing the x, but it's changing the y, so I need that negative sign outside my function. Going left 2 means that's happening inside the function, since that's a horizontal shift, and I would be subbing in a -2 then, which we can simplify down in a little bit. And then a vertical stretch by 3, this is my a value that I want to multiply in front of the function. Since I already have a negative sign, I'm going to multiply not only by the negative, but also by 3, so I can rewrite this as multiplying by -3 then. And of course, we can simplify this to be -3 absolute value of x plus 2 as our final answer. So in this video, we learned about what our different transformations were. We have our vertical shifts, our horizontal shifts, we have our reflections over the x-axis or the y-axis, and we also have our vertical stretches or compresses.